Okay, good afternoon. So I'm gonna just try my best to finish the lectures on real-time systems so that we can move on to memory address translation. So in the previous lecture, we were talking about real-time scheduling policies. The first one that we saw was rate monotonic, and then we saw an example. Now let's so this is the example that we saw. So the same example that round robin failed to produce a schedulable, a feasible schedule, rate monotonic was able to do so. Now, is rate monotonic able to schedule every possible workload? So to answer that question, let's look at another example. So in this other example, I have three tasks. Now, as before, T1's priority is more than T2, and T2's priority is more than T3. The reason is T1's period is shorter than T2, and T2's period is shorter than T3. And rate monotonic prioritizes the tasks based on their period. Now, as before, let's put on the markers for when each task has a new job. So these are the markers, assuming that everybody will get a new job at time 0. The highest priority job is from T1, so we're going to schedule T1. Then we're going to go to T2. Now, the reason that we're going to run 2 time period for T2 is because at this point, at time 2, T1 doesn't have any tasks. So we have, it doesn't have any job. So we have a job from T2 and we have a job from T3, but then T2's priority is higher than T3, so we continue running T2 until time 3, at which point a new task, a new job from T1 comes and it has higher priority, so we run that. At this point, we're done with the job from T1, we're done with the job from T2. We only have one job in the system from T3. So we're going to run one time period or time quantum for that one until we get a new job from T2 with higher priority. We're going to run that one until we get a job from T1 with higher priority. We're going to run that one. And then we're going to come back to T2. At this point, again, no job from T1, no job from T2. So we can go and run from T3. But then, unfortunately, at this point, T3 has already missed its deadline. Okay, so we found a schedule that, or we found a workload consisting of T1, T2, and T3 with the specific execution times and the specific deadlines and periods that rate monotonic has failed to produce a feasible schedule because T3 missed its deadline. So generally speaking, there is a test to be done to see if rate monotonic can produce a feasible schedule. So the formula is in front of you. This is basically the utilization of each task. So execution of each task divided by its period. If you remember, this is basically the utilization. If you want to think about this, think about giving a single CPU to a task. And now we want to measure, so there is no other task in the system, there's just this task. Every time a new job comes, it runs immediately. Now we want to see how much this task utilizes the CPU just by itself. And this is going to be its execution time divided by its period, right? Because at every period, it's going to get one task and that task, sorry, one job, and that job is going to run for its execution. So the CPU utilization for this single task is going to be EI divided by PI for task I. Now, if I have n tasks in the system, I can sum up their utilizations. So this is this term, the left-hand side is the sum of utilization of all tasks. Now, if this number is less than n times 2 to 1 divided by n minus 1, so if this inequality holds, then rate monotonic is guaranteed to produce a feasible schedule. If this does not hold, then we cannot say anything, right? There are cases where this inequality doesn't hold, but we are able to produce a feasible schedule. And there are cases where this inequality doesn't hold and we are not able to produce a feasible schedule. So this inequality only tells us when we are guaranteed to produce a feasible solution. It doesn't say anything about when we are not. So let's look at examples. So if you plot this one, so let's say this is f of n equals n times 2 to 1 divided by n minus 1. So if you plot this, oh, actually, sorry, it's not that plot. No, it is. So this is the bound that you're getting. So if you put 1 in this equation, it's going to be 1. So if you put 1, it's going to be 1, 2 minus 1, that's 1. So that's this point, and so on and so forth. So you can put different ends and get these points. So as you can see, this bound is decreasing. So as the number of tasks in the system increases, this utilization bound goes down. So if you have, for example, if you have a workload with, I don't exactly know where these numbers are assigned, but with these many tasks, and the sum of utilization is here, then you're guaranteed that that RM will work. If the number is here, then you don't know. It may or may not work. So this is the example. This is this example. So for the example where we failed, so if you look at that, if you put these numbers, the utilization of task 1 is 1/3, the utilization of task 2 is 2/5, the utilization of task 3 is 2/8. So if you sum them up, you get this number. Now, if you put n equals 3 in that equation, you're going to get 0.78. So this number is higher than this number. So there is no guarantee that RM works. And in fact, we just checked and it doesn't work. OK, so next, we're going to talk about another example from a different class. So RM was from the static scheduling class. Now we want to talk about dynamic scheduling class, and EDF is an example of that class. So EDF is dynamic. It prioritizes tasks. It actually prioritizes jobs based on their deadline. So the earlier your deadline is, the higher your priority becomes. Now, why is it dynamic? Because it's assigning a priority to jobs and not tasks. And the priorities that are assigned to jobs are going to not change over time. So in a static, we're going to assign priority to tasks. So any job that comes from a specific task, they're going to have the priority that the task has. And this priority is not going to change over time. Very similar, I mean, exactly like RM. So in RM, we were prioritizing tasks, and every job in each task has the same priority as the task has. Now in dynamic scheduling, we're going to assign priority to jobs. So different jobs from the same task might have different priorities, but then the priority that you assign to a job should not change over time. So as long as the job is in the system, its priority should be constant. And then fully dynamic, which we will see, is going to have to assign priority to jobs, but the priority will change over time. So I got a question, what's the online in dynamic online? I was avoiding to talk about it, but now that you're asking, so we also have another subclass. So if I were to do it top down, so real-time scheduling has two subclasses, online and offline. Now, offline is absolutely not interesting because offline means I know my task set, and I set up the schedule offline, so there is no surprise basically. So I know my tasks, how they come, when they come. I know everything, and I set up the schedule for them. I can schedule them any way I want. No, no specific rule. I can just set up a table and say at time 1, this task runs, at time 2, this, at time 3, this one, so on and so forth. In online, we don't make any assumption about knowing when our tasks or our jobs come, right? So they could come at any given time. You for example, if you have what was it, the sporadic tasks. So sporadic tasks come at random times. An offline scheduler cannot deal with sporadic tasks because they're just randomly coming. But online scheduling policies don't make any assumptions on knowing when jobs come, right? For example, in RM, I have the period, and based on the period, I will set the priorities for my jobs, right? Or in EDF, as we will see, I don't care when my task's coming. I just look at their deadlines and I set their priority to their deadlines. So I don't make any assumption before system starts running on knowing my tasks, right? So the system starts running, I get a task, I get a job, I assign a priority, and I continue running because I didn't make any assumptions on knowing who comes, who doesn't come. In offline, I do. So in offline, I have to know everything beforehand and then make my scheduling in a table, and everything is just written on this table, and then we're going to execute based on that. Now online, as we saw, is going to be a static, dynamic, and fully dynamic. So we're not going to talk about this offline because we don't care about it. So we're just going to be on this online part. Okay, publish. So in RM, since utilization is capped, is that an example of trading off performance for predictability? Not really. So it's kind of like just a downside of RM that it can only guarantee feasibility for certain utilizations. As you will see with EDF, this bound is much higher. It's actually 1. So as long as the sum of utilization is less than 1, then you can schedule, you can produce a feasible schedule. We'll get there. Okay, so EDF is optimal with respect to all online schedulers. So if there is a workload that any online scheduler can produce a feasible schedule for that workload, then EDF can do that too. Therefore, EDF is optimal with respect to all online schedulers because it's as powerful as any other scheduler in online scheduling class. So let's run an example for this. Let's this is the same example that that RM failed. So the same 3 tasks with a priority with period 3, 5, and 8. Now we're assuming that everybody is going to get 1 task at the beginning. Let's run this. So at this time, at time 0, I have 3 jobs in my system, 1 job from each one of the tasks. Now, which job has earlier deadline? Well, the earliest deadline I have is this one. So job 1 of task 1 has the earliest deadline. So I'm going to run that one. Now, next, once I'm done with this, I have T2. So I have the job from T2. And that job has a deadline at time 5, and a job from T3 has a deadline at time 8. Well, 5 is less than 8, so I'm going to run T2. Okay, now at this time I get another job from T1. Its deadline is 6, whereas the deadline for job in T3 is 8. So the one with 6 is earlier, so I'm going to run that one. Now I don't have any other job but T3, so I will run it. Okay, now this is where EDF deviates from RM. Now at this point at time 5, I'm going to get a new job from T2. RM would run this job because T2 has higher priority than T3. But in EDF, the new job that comes from T2 has a deadline at time 10, whereas the job in T3 has a deadline at time 8, and 8 is coming sooner than 10, so I will continue running T3. Okay, now T3 is done. I have a job from T2 and a new job from T1. Well, the job in T1 has a earlier deadline, so I'm going to run the job from T1. Then I'm going to run the job from T2. At this point, I'm going to get a new T1 job. I will run it, and so on and so forth. So if you run this to completion, you will see that. So I think you need to run this for, if I'm not mistaken, what's the common multiplier of 3, 5, and 8? I think it's going to be the multiplication of all of them. But if you run for the common multiplier, you will see that all the deadlines are met, and then it repeats itself. Okay, so now we're going to do the same thing that we did with RM. So what about EDF? So there is a theorem that says EDF can produce a feasible schedule for any workload with sum of utilization less than 1. So as long as the sum of your utilization is less than 1, then EDF can produce a feasible schedule. So you can get better than this, right? Because if the sum of utilization is more than 1, meaning that, you know, I run each task by itself and I see how much they utilize the CPU, and then I add them up and it's more than 100%, well, that means that no single CPU can run these tasks, no matter what your scheduling policy is. But if it is less than 1, then EDF will be able to produce a feasible schedule. So this is why it is optimal with respect to any online scheduler. And if it is the case that the sum is more than 1, then the system is overloaded. So once the system becomes overloaded, meaning that you have more tasks than your CPU is able to run, then, well, EDF cannot do anything. But unfortunately, EDF starts behaving weirdly when overloading happens. So let's look at an example where EDF doesn't do what we would expect it to do when the system is overloaded. So here's an example. Let's say that I have this task set, T1, T2, T3, and T4, and the periods are 4, 5, 6, and 7. So if you can see that the utilization for this is 3/4, plus utilization for that guy is 3/5, plus the utilization for that one is 1/2. The utilization for the last one is 3/7. So I think the common multiplier here is what is it? 30. It's 4 times 35. So it's going to be 3 plus. Oh no. I guess it's obvious that this is more than 1 because this is more than half and this is half. So this is definitely more than 1, right? So this is definitely more than 1. So EDF cannot schedule this because the utilization is more than 1. Okay, so how does EDF work for this? Well, the first job that will be scheduled is the job from T1 because it has the earliest deadline. So T1 runs. Then the next task that will be scheduled is looking at the deadlines. The T2 job has deadline of 5, deadline of 6, deadline of 7. Okay, so we're going to pick T2, but then T2 is going to run for 3 time periods. So after 2, it's going to miss its deadline because the deadline was 5 and we're already 5 and we haven't finished this job. So T2 will miss its deadline. So we're going to put it aside. Between T3 and T7, we're going to pick T3. We're going to run only 1 unit and it will miss its deadline. And then we're going to jump to T4 and it's too late. So T4 also misses its deadline. So with EDF, only T1 can meet its deadline. Now, if you look at this, although the system is not schedulable, but there is a schedule that is better than this. So here is a better schedule. I can run T1 and T3, for example, or T1 and T4. And both of these two schedules at least I will meet 2 jobs deadlines, right? So both of these 2 are better than this one. But again, EDF guarantees schedulability as long as the system is not overloaded. The moment the system becomes overloaded, then EDF behaves in an unexpected way. So it doesn't produce the best possible outcome when the system becomes overloaded. Okay, so now our last example will be from the class of fully dynamic. So you should expect to see priorities being assigned to jobs, and the priorities should change over time. So that's what's going to happen. So in order for me to define LLF, so what it does is it assigns priority to job based on their laxity. Now, what is laxity? Laxity means how much time do I have left until my deadline. So that's the definition of laxity. So let's say that you have an absolute deadline at time D, and you have a remaining execution at time E. Remaining execution time of E. Your laxity is basically D minus T minus E. So let's look at an example. Let's say we're at time T, and let's say that the job has E execution time. So the execution time of the job is E, and we're at time T, and the deadline is at time D. So if I start running the job right now, it's going to take E time to finish it. Now, from when I finish until the deadline comes, this is my laxity. Now you can see that the more laxity a task has, the more flexibility the scheduler has, because if the laxity is large and long, it means that I still have time to finish this job. I can put it on a back burner and do other jobs that have shorter laxities. So the shorter the laxity is, the less flexibility I have. If this laxity is 0, what does it mean? If the laxity becomes 0, it means that, let's say this is time, let's say I'm at time T, and if I execute this, it's going to take E. Laxity equals 0 means that D is equal T plus E. So basically, if I start running the task right now, I barely finish the task by its deadline. So I just right at the deadline, I finish the task. So laxity equals 0 means the highest priority. I have to execute my task right away. If I wait for another second, I will miss the deadline. And if the laxity is negative, it means that I've already missed my opportunity to run this task because the laxity is now negative. So hopefully that explains what laxity is. So this is the laxity. So now we're gonna look at each job's laxity and give higher priority to jobs with higher laxity. Now you can see that this laxity is a function of time, right? This is L of T, so it depends on time. If you look at the laxity of a job later on, it changes. So therefore, the priority of jobs change over time because their laxity changes over time. So that's why LLF is a fully dynamic scheduling policy. And similar to EDF, LLF is also optimal with respect to all online schedulers. So LLF is as powerful as EDF. But as we will see, it's just more complex. So if you have a choice, you will choose EDF rather than LLF, because LLF is a little bit more complex to run. It's also very impractical to implement, because you could have a situation where you have two tasks with the same laxity, and then you will have to then context switch between them again and again and again, because if two tasks have the same laxity, you're going to run a little bit of one of them, and then the laxity of the other one becomes shorter. So then you will have to switch to that one. And then again, you will have a tie. And then you run one of them, and the other one becomes higher priority. And then you have to context switch. So with EDF, if you have equal deadlines, you will choose between them and then you run to completion, right? But with LLF, because laxities change over time, you will have to context switch, because the priority of the one that you're not running increases because its laxity decreases. So over time, compared to EDF, LLF requires a lot more context switching. So if you want to have exact LLF, it's very similar to exact max min fairness, where you have to just run one instruction from one of them and then another instruction from another one, and so on and so forth. And if you want to do approximation, so run them for a time quantum, then you will have to do context switching again. So that's why usually LLF is not used. It's just a theoretical benchmark. So here is an example for what I just explained. So let's say you have two tasks, T2 and T3, and let's say at time 0, we're going to see what their laxities are. So what is the laxity of T2? The laxity of T2 is 3, because the deadline is at 5, the execution is 2, so it's going to be 3. This is the laxity. The laxity of T3 is also 3. So both of them have the same laxity. Now you choose one of them according to whatever criteria you have. Let's say randomly we pick one of them. So let's say we run T2. So you're going to run a little bit of T2. And as you run a little bit of T2, the laxity of T3 goes down. So you have to switch to T3, and then you have to switch to T2, switch to T3, and so on and so forth. So as you can see, and this is actually a relaxed LLF. In actuality, you should just execute one instruction from each one of them, one instruction back and forth. But let's assume that you do it with time quantum. Then, as you can see, you will have to do a lot of context switching. So here, at this point, for example, the laxity of T2 hasn't changed, but the laxity of T3 has gone down, because now you have less time with the same execution. So the execution time hasn't changed, but you have gotten closer to the deadline. So therefore, the laxity goes down. Therefore, T3 becomes higher priority. You have to context switch to T3. And then you run the T3 job, then you will have the same laxity. You either continue or you context switch. You randomly choose. You run one of them, the other one becomes less lax. And then you have to then context switch again and again. OK, so let's put all three that we have seen so far together. So rate monotonic, earliest deadline first, least laxity first. So among all of these guys, rate monotonic is the simplest to implement, because each task has a deadline, and sorry, each task has a priority, and that priority is given to all the jobs from this task. So it's very easy to implement. There is not much dynamic activity going on, so it's easy to implement. Unfortunately, the downside is that it supports low utilization. So when you have high utilization, then RM cannot guarantee feasibility. Now, earliest deadline first can support all the way to fully utilized system, but the downside is that it could misbehave if your system becomes overloaded, and it's less simple to implement. So previous years, so in all terms that I taught, I don't actually remember last term, but we always had P4 for the labs, and in P4 students were implementing EDF. So if you look at your starter code, you see the priority 0 is reserved for real-time tasks. So in the past iterations of the course, we had P4, which was implementation of EDF. So you're lucky. I just ditched it because already the lab was too hard. So anyhow, I don't know. I read some reviews of the course, and those who actually implemented this part of the real time, because this is actually where the system becomes real time. So far, you're doing some, for R1, R2, sorry, P1, P2, P3, you're doing somehow general purpose operating system. But in P4, students it was the first component of the system that was actually real-time operating system. But unfortunately, I had to get rid of it. Anyhow, if any of you is interested, just reach out, and I might be able to give you the manual if you want to do it by yourself, which I actually recommend. If you're interested and you have time and you want to play with it, I think it's a good investment of your time to do this. But anyhow, now LLF also provides full processor utilization, but it's impractical. So practicality is an issue with LLF. Okay, now let's talk about scheduling mixed periodic and aperiodic or aperiodic tasks. So if you have aperiodic tasks, so these are the tasks that come randomly and they don't have any deadline. So they don't have a period, they don't have a deadline. One idea is to just put them on back burner, and one idea is to just run them as soon as they come. So the first idea is to run, The first idea is to run them as soon as they come. So basically give them the highest priority in the system. So as soon as an aperiodic task comes, start running it. Now, this is good for aperiodic tasks, but it has negative impact on periodic tasks because you're jeopardizing the periodic tasks. The second idea, as is mentioned here, is to give them the lowest priority. So as long as you have periodic tasks, run those and then go to your aperiodic tasks. Now, this is bad for aperiodic tasks, but at least it doesn't impact your periodic tasks. Now, one thing to mention, at this point, you should ask yourself, what are the examples of these aperiodic tasks? So going back to the discussion we had with interrupt handling, if you remember, I said the solution 3 was when an interrupt happens, you run the interrupt handler and you create a new task to go and deal with whatever this interrupt was. So the new task that you create is an aperiodic task because it came randomly, it doesn't have a period, and it doesn't have a deadline, right? You just created it. So this is one example of aperiodic task. And you can just see why someone would choose the first one, the first idea, which is giving these aperiodic tasks the highest priority, because these are usually your interrupt handlers. So you want to deal with them as soon as possible. You could also see why someone would choose the second one, because they might say, okay, I don't care about these interrupts. I have jobs to do. And then once I'm done with my periodic jobs, then I go and see what the interrupt was. So both of them could be valid based on systems that you're designing. Now, a better idea is to kind of, buffer these tasks and somehow give them fake period and fake deadline, because they don't have it. So if we can just assign them some notion of period or some notion of deadline, then we can use our already existing real-time schedulers like RM, like EDF, or LLF to schedule these tasks like any other periodic task. So this idea is called, we call this a periodic server. So this server is basically a interface that is going to represent all our aperiodic tasks. So when our aperiodic tasks come, we're going to buffer them in a queue, and we're going to call this a server. And now we're going to treat this server like any other periodic task. Now, we're going to assign this server a period and a budget. And we're going to run any buffered aperiodic task in the server as long as the server has a budget. So let's go to the specifics of this. So now the way we assign period and the way we assign budget will identify different methods. So different scheduling methods would set period and budget differently. Now, again, the overall idea is this. So we're going to put all our periodic tasks in a queue, and we're going to have a representation for all of them. We call it a server or a periodic server. Now we're going to assign a period and a budget to this server, and then we're going to treat this server as any of the periodic tasks because it has a period. So it will be scheduled, this server will be scheduled as any other periodic tasks. And whenever it's scheduled, it runs any task that it has here, as long as it has a budget. Okay, now let's look at different options that we have for this server. The first option is called polling server. So in this one, periodic tasks and the polling server, we're going to call it PS. We're going to schedule them according to RM. Aperiodic tasks are going to be queued, as we mentioned, in a queue, in a separate queue, until we invoke the PS. So we schedule PS. Now, depending on the period that we assign to PS, at every given period, the PS will start executing its jobs, its aperiodic tasks, and then if there are no tasks in the queue, or if the budget expires, then we're done with the PS server in this period, and we go to our other periodic tasks until next period. So basically, PS is treated as a regular periodic task, and it's going to be scheduled with other periodic tasks. Now, usually in polling servers, we're going to assign PS the lowest period in the system. So we're going to look at all the other periodic tasks in the system and see what their period is, and then assign PS a period that is less than everybody else. So when we do this, this means that we're going to prioritize PS over everybody else, right? Because we're giving it the highest priority. Now, this is not, this you can play with. You can give PS any period you want, but usually when you're using this method, you assign PS the highest priority, meaning that you assign PS the lowest period. But again, depending on your system, you can actually assign different periods. So let's run an example. Let's assume that our system has a single periodic task. It's T1, its period is 2, and its execution time is 2. Now let's assume that I have a PS, and let's assume that I have assigned a period of 5. So in this example, I didn't make my PS server to be the highest priority. I gave it a lower priority by setting its period to 5. Again, you can set the period of PS as you wish, depending on your system. Now, in this example, I have set it to 5, and now this 2 here is the budget. So I've assigned a budget of 2 to my polling server. Now, let's assume that these are my aperiodic tasks. So as you can see, they're coming randomly without any period. And let's assume that their execution time is shown as the length of the box. OK, so now let's run RM on this. So initially, I have T1 and PS. T1 has a higher priority, so I'm going to run P1. I'm going to run T1. Now, at this point, I'm going to switch to PS. Now, PS has buffered 2 tasks so far. So 2 tasks have come. So PS will run those 2 tasks. And in this example, before the budget expires, so the budget was 2, so PS could have run for 2, but it didn't have any more tasks to run. So all of a sudden, it's done. So we're going to just assume that PS is now done, and it's going to go for its next period. So we will, in this period of time, there is no task in the system. So then a new job from T1 comes. I start running T1, the job from T1. Now, at this point, a new PS comes, a new PS period starts, and the budget is set to 2. Now, at this time, I'm going to switch back to PS, but PS doesn't have any jobs, any new arrival. So there is nothing in the queue. This means that we're done with PS for this period as well. So PS is done. Now, these new tasks that come, because PS is not going to be scheduled anymore, they're going to be queued. Now, next time period is here. I'll run T1. Now, at this point, when I switch to PS now has 3 jobs, right? So it starts running them. And once it's done, we're done. And again, another task here, another aperiodic task comes. And even though the budget was 2 and I could have executed this, but because I got done with my previous tasks earlier, I put the PS server aside because it doesn't have any job anymore. So this new arrival gets queued again for the next period. So hopefully this explains how polling server works. Now, as you can see, this kind of is sort of unfair to the aperiodic tasks, because the server did have a budget, but it didn't end up using it. So this graph that you show I put here is the budget over time, right? So at the beginning of the period, you get your budget, and then as you start running, your budget goes down. The moment you're done with your jobs, your budget goes to 0, and you wait for the next period. Again, your budget comes up. You get a schedule, you don't have any tasks, so your budget goes to 0. Again, you go with budget 0. At the beginning of the period, you get your budget up. You start running, you're done with your tasks, your budget goes to 0, and so on and so forth. So this is how PS is working. Now, one option to kind of improve on this and make PS a little bit better for aperiodic tasks is to, instead of going to budget 0 the moment our tasks are done, we preserve the budget for the PS, even if it doesn't have any job. So PS saves its budget, and the moment it gets a aperiodic task, if it can be scheduled, it will be scheduled. So this is deferrable server scheduling, so it's called DC. So running the same example as before. So all we have changed is we're going to keep the budget for the server. So like before, so far so good. Now here, oh my God, sorry, this USB is very sensitive to touch. So okay, so at this point, oops, I guess it's good to put this as well here, the budget. So the budget goes up at this time. You get your budget. Now you get a scheduled here. And when you get a scheduled, your budget goes down, even though you don't have any jobs to run, but you don't give up your budget. So when you get a task, you run that task because you still have a budget. Your budget didn't go all the way to 0. Now time goes by here. Now T1 has a higher priority, so T1 runs. And at this point, you start running. You have these two, you run them. You don't give up your budget. You keep your budget. So then when you get a new task, you can run that task. So on and so forth. So that's the idea behind DC. So I got a question. Why would the last aperiodic task be executed? It has arrived after your PS finished. I assume that you're asking about, yeah. So again, in PS, the last one wouldn't be executed because the PS server has finished and it's put aside. But in reality, we did have budget. So our budget was 2, and we haven't used our entire budget. So that's where the DC comes. DC says, okay, as long as I still have budget, I'm going to keep my budget. I'm going to preserve my priority and wait until I have a task. And when I have a task, I will use my budget if the scheduling policy allows me. Okay. So there is another one, total bandwidth. I don't know if I want to. Okay, let's pause here. I'm over time. So unfortunately, I didn't get to finish this, and there are a couple of more topics to be covered. So next on Tuesday, hopefully I get to finish this first and start talking about address translation. So thank you for coming to the lecture, and take care, be safe. Talk to you on Tuesday. Bye.